Okay, so we'll continue. We're delighted to have Ankit Anand and Abbas Mehrabian, both from Google Deepmind in Montreal, to tell us about theorem proving and disproving using machine learning.
Hi everyone, thanks for inviting us. It's a privilege to be here and interacting with you all. And yeah, this is some of the work which we have been doing in Google DeepMind Montreal office, especially from we started this. I think this is the work of last 3-4 years. Even something when even the language models had not gotten that much hype at that point. So we started with the theorem proving, and then we went to disproving, and we had collaborated with Adam on some of this works. So I have my colleague Abbas with me, who would talk about the second part, but I would get initiated on the automated theorem proving what we did. So it is mostly interesting part is that how the machine learning compares with the a lot of work has gone into using classical search approaches in both these methods, in disproving or finding door bounds, and in automated theorem proving as well, and how we applied machine learning and how does it compare. So yeah, AI and maths in the contemporary world, I think in the last 3-4 years, it has created a lot of hype. Especially, I think it has a lot of mathematics community has taken notice into this, and it's kind of a shameless plug of a lot of Deepmind works. But yeah, I wanted to highlight a few of the works here. The first work was from the Alex Davis and the group, where they developed the conjectures were proposed by using methods in AI, and then mathematicians collaborated with them to prove some of those conjectures in knot theory and so on. Then we had work on alpha tensor on matrix games, where the AlphaZero algorithm was used to find the tensor decompositions. And recently, in the last year and this year, we have gone to the fun search, where we are using language models to discover mathematical objects. And more recently, early this year, we had alpha geometry, where basically we used the AI methods for solving Olympiad level geometry problems. And I think this slide has already become outdated with the alpha proof thing, where the AI got on to win a silver medal with different methods. And although I go with the caveat that there was a lot of mathematical knowledge involved in there. But yeah, the whole idea is that AI and maths community is coming together, and that is why probably these programs and workshops are coming together, which is super nice that we have cross-pollination in different fields. So in this talk, and in the past few years in our group, we have focused on AI for mathematics from two angles. We looked at initially theorem proving, and there are other people in DeepMind as well working on theorem proving, and also on the disproving side. So when we started with the proving side, we thought the disproving is also probably slightly easier maybe than because it is just you may need to find a counterexample. But it turns out it is equally or even more harder problem, and Abbas would give a detailed flavor of what we ended up with there. So for the today's talk, what the part I'm going to talk about, this is from ICML 2022 work. It is kind of a pre-language model era, and I joke with that this is a very old work, but it's only 2 years, which has become a very big time in machine learning. But it had some very interesting lessons, and I'm really proud of this work, that how we came up and how we started this. And I think it has still many areas where these ideas could be applied. So it's very interesting. And I think the inspiration was from our idea in reinforcement learning, what we call hindsight experience replay, to do automated theorem proving. And yeah, it was published at ICML 22, and AI for theorem proving, there is a small workshop and conference there, so published there. So I want to start with a quote from Bertrand Russell. And yeah, this happens when we converted Google Slides to PDF, so the formatting is slightly off, but I hope that's okay. So the fact that mathematics is the symbolic logic is one of the greatest discoveries of our age. So logic has been discussed in the AI community a lot in the past as well, and I think the AI and mathematics community has come together. And in 2018, or I think it's 2019 or 2020, this challenge was proposed, I think with a few people from different orgs, that where the task was that AI would be given formal description of IMO problems, International Mathematics Olympiad problems, and the aim was that the challenge was to win a gold medal. And it seemed very unlikely. I was working in that field in 2019, the language models was not the mainstream of use in theorem proving. it seemed like, yeah, it is very far. Like the IMO requires quite a bit of ingenuity and all. But here we are in 2024, and AI had achieved very close, like I had achieved a silver medal and missed gold medal by a point. So yeah, so this area has been coming up in the last 3-4 years, and from here we started this project. And since these were like, we were not experts in logic. We were coming from more, means I had worked in a bit of logic, but like I was more coming from machine learning background. But the idea was where we should start from the logic. So there had been a lot of work in the SAT system. So we started with the first order logic. There was first order logic, propositional logic, and higher order logic. So we started with the first order logic. It was simple to understand. It has a lot of interesting mathematics domains, like very famous conjectures, like in number theory and all, could be easily encoded in the first order logic. And yeah, like it has applications in verification and a few other things. And the other thing was that it had very strong baselines. And as you know, like in the Deepmind is really interested about like games and chess and so on. So we found when we ventured into the first order logic community, there are stockfish-like baselines. So like there were heuristic provers, which were there, and there was a competition, and we like competitions. So you're like, yeah, this is the nice place to enter, and it was easy to understand compared to higher order logic. So we started with there. So just to get like warmed up, I will probably like, I'm sorry if people are experts here in logic. I am not, but so I will give a brief background of how the first order logic systems work and what is our setting. So basically, yeah, the problem is you are given a proof system which has certain rules, what you can do, what is allowed to do. And you have to prove a theorem which is formalized by humans. Like, so you take a mathematical theorem, you have formalized in the first order logic, and then there is a proof system. I will come to the detail of what is a proof system. And our hypothesis is that this is a very interesting domain. So deep learning has definitely proven to be very great where enough data is there. But the issue is here that we don't have that much data in first order logic. So we started with a lot of like systems that can use synthetic data to generate artificial theorems, where if we make progress, we can actually make a mark in the like the theorems which actually matter. So we went there. So this is the setting and how it looks like. So the first order logic has quantifiers like universal and existential quantifiers, like you talk about for all there exist and so on. So for example, a typical conjecture would look like this, that there exists a y for all x, where py implies px. And you could be given a few axioms on the top, and from those axioms, you and the conjecture, you want to prove the conjecture. And how, so there are many proof systems there. So but like more popular or like the more systems which work nice are like, which what they do is that they convert the conjecture into a negated clausal form, like and what we call as CNF, and in a syntax of like a first order logic, what is called TP. So then it looks like this. So you don't need to like go into the details of this, but yeah, it looks like this. I just wanted to give a flavor of that. You had a py and this will like, so you basically get rid of the existential quantifiers and so on, and the conjectures look like this is the and of different terms. So and of ors basically in a CNF form. So you have different formulas which are in clausal form, which have ors, and then you are taking the and of those, and somehow from these formulas you derive new formulas and so on, and your goal is to achieve false, basically contradiction. Because what we do is that we are negating the conjecture, we and it with the axioms, and we are saying that all these together implies false, which is a contradiction, and this means that the original conjecture was true. So yeah, these are like some axioms of group theory are encoded in the first order logic. There's a hypothesis, there's a conjecture, and that is how it looks like in like this DPTP syntax, which has like the predicates and so on. But yeah, like if you like, this looks a bit like opaque, don't worry about it. We don't need to worry too much about the details of the first order logic. So what everyone uses, like the most one of the famous like forms of proof systems in first order logic is what resolution calculus. The interesting part of resolution calculus is that it only has two operations. So with two operations, like the theorem is that like that you can, it's what we call as refutationally complete. That you can basically, if a thing can be disproven, you can basically like disprove it. Like if you keep applying these formulas and you exhaust all possibilities, you can disprove like basically the negated conjecture like always, that if you have exhausted all the possibilities. So the two formulas here are like what we call resolution and factoring. So resolution is like this, that if you have two formulas which are not px or qx, and then you have the second thing is you take an and with that, so you can derive like which is p of c. So if you take the and of these two terms, you can derive a new formula which we call here as q of c. So basically we have substituted, we have did a substitution of x goes to c in the first formula basically, and then p of c or not of p of c becomes cancels out, and then you have q of c. So you have derived a third formula out of it. So this is one rule. So you keep applying.
What's the meaning of the vertical line?
Or, yeah, logical or. Yeah, so it is in the first order logic we have like, we have this. Yeah, that's right. Yeah, it's like, both the ways are used like that. Yeah, and the other thing is factoring. So the resolution works on two axioms, like two clauses, and gets a new clause, while the factoring, you have one clause and you simplify that clause. So for example, if you are given px or p of c, where x is a variable here, while c is a constant, or q of x, you can derive a new formula again by substituting x goes to c, p of c or q of c. So again, for simplicity, basically what we are doing is that we are given some formulas, we are deriving new formulas out of it, and you can keep going doing this for all the formulas. And if you hit false, you are done. So that is the goal. But the interesting part is that these two rules are sufficient. So if you keep applying these rules again and again, and if you will definitely hit false for a thing which is like so you can prove any theorem, which is actually if it is a theorem, then you can prove any theorem in this system. So yeah, so for like using these rules, there have been a lot of progress in like search community and the theorem proving community over the years, that how we should apply these rules, which two formulas we should pick at any given point to get a new formula, and so on. Like the space of the formulas grows exponentially, like because you are deriving new and new formulas, so your space is increasing, how to manage that. So one of the algorithms which everybody uses and the state of art prover uses is called saturation. So it's a simple, it's like a A* algorithm, but in this structure. So what we do is we are maintaining two things. We are maintaining a set of processed clauses, what we call as processed clauses at the top, and unprocessed queue at on the left here. So what you do initially, so you have different clauses which are like ORs of different things. What are the formulas there? Like axiom 1, axiom 2, negated conjecture. You put everything in a unprocessed queue. Now for each of these clauses or formulas, you would assign a cost somehow. Now the simplest cost could be what is the length of this clause. Because we want to reach false, so maybe a good idea is that the smaller clauses are better, because we want to reduce the clauses, or we want to derive new things false out of it. So that could be one of the costs. But I think it is like a magic, or like how you assign the cost to different clauses is a question here. Like that is, so there is a cost function associated with each clause. At any given point, we pick a clause of initially the set of process clauses is empty. We pick a clause with a minimum cost, and then say means initially this would be empty, it will go there directly to the processed queue. But if say the processed clause process set has some clauses, so what you will do when you pick a thing with the minimum cost, you basically check a redundancy check. It is not complete, because then it becomes equivalent to a theorem proving problem. So you will check with that if this clause 1 subsumes any of the process clauses. If it subsumes, basically it is more general than any of the process clauses, then you would throw that clause away and put this in there. And if it is subsumed by anything else, then you would throw this away. And if it is general, that it is not subsumed by anything else and it doesn't subsume anything, you put it back, you put it into the processed set. So things keep going into the process set, and process set is like a kind of a nice set. It's a smaller set you are maintaining. And what you do additionally, you not only add this, but you also do resolution and so you do factoring at this point. So you do resolution with all the existing clauses in the process set. So basically, when say you are adding CL1, because new things you can only derive by resolution or factoring. So we don't want to do resolution with everything. So we are maintaining a nice minimal set in the process set. When we pick a new thing, we do resolution with only those sets to derive new things and put those back in the unprocessed queue. So the derived clauses, so you put this clause up, but you derive some new clauses by resolution and factoring those operations by the resolution between this clause and the process set and put back in the unprocessed queue. And so you keep doing this process where you're sampling from the unprocessed queue with the cost. So the new clauses are assigned a cost and so on. Is that part clear? So yeah, so you do some redundancy checks. And yeah, it could be very, very smart checks, but it could be as simple as like as so. And again, the cost function could be simple or smart. And a lot of people in machine learning, they have tried to learn this cost function now. So because like the most of the heuristic people, what they were doing is they were trying to come up with nicer and smarter ways to assign a cost. What could be the nicer? What is like the simplest one? The simplest still the cost function which works pretty well is the length of the clause, which works pretty well. But people have come up with very, very smart cost functions. But the machine learning people, when they entered, so they were like that, we will give a neural network this clause to a neural network, and the neural network will assign us a cost. And I will go to that how they do. But this is the algorithm everyone uses with this. And this is how the World Cup of first order logic theorem proving looked like. Yeah, I think it is still 2022. So they had this different categories of the competition. FOF is simplifying first order logic formulas. Then there are a few other categories. And there is this prover called Vampire, which is winning this competition since last, I don't know, 20 years or so. So it is like it's crushing everything, and it doesn't use any machine learning. It is, I think the recent versions use machine learning, but like the most earlier versions were very smart heuristics they have gone to. It's a very solid prover. It is in C++, super optimized, and so on. So you're like, yeah, we want to get here and we want to beat like Vampire, and like there are other provers as well. We could not compare with Vampire at that point because of we were Google, and it was not allowed to use it for or compare for even run it for commercial purposes. So we went to the next best thing, which is also pretty close to it, called eProver, which had the good licensing requirements for our comparison, and we did with that. So, but like our goal was that okay, this is the stockfish of theorem proving. We want to go ahead on this. So as I told, this cost function could be learned. So this bit, both these bits could be automated or like in some way. But we stressed on like, okay, the cost function could be learned, which people had been doing before us. So one simplification of saturation, how you want to look at it is that, like if you forget about these queues and clauses, you have the axioms and a conjecture at the top, and you derive new things out of it. So the nodes here define the clauses. So the bottom nodes, like after the top level, denote what new things you have derived out of the existing axioms. So, and basically you keep driving new things until the point you reach contradiction. Once you have contradiction, so the yellow highlighted path, basically the path from this node, basically a subgraph from this node to all the nodes which covers on this subgraph, those become part of the proof. So the remaining things you derived were not used in the proof, so they are redundant. But while like this part is the useful part. So how people use machine learning, like this was before us, what people were trying to do was that once they reach a contradiction, so they would keep doing this with different things like simple, or like they will just like simply by length or by searching randomly. Once they have hit a proof, a contradiction, these clauses become part of the proof. So all these clauses are good clauses or useful clauses which are helpful for theorem proving the theorem. So these become positive examples. So we do supervised learning at that point. So all these clauses become positive examples, and the remaining clauses become negative examples. So the things which were futile. So this is how people were using it. So basically, given a clause, they were like trying to predict whether it's good clause or bad. And in machine learning, we do this with the probability. So the cost now becomes the probability at that point. So the cost of a clause, because you learned a classifier at that point, and the cost of each clause would be the probability of that classifier being useful. So we also looked at from the RL perspective. We were very motivated to do RL here, and so we're like, yeah, like means we don't need to worry about the supervised setup. We can go ahead with the RL setup, but then the issue is that the number of actions. So that each action here is a pair of nodes, and the number of actions when we tried RL algorithms were increasing very fast in saturation. So it's because it's quadratic. It's the action space with each new quad clause added. You are basically increasing the action space by the size of the state at that point. So the action space was increasing very fast. The state space was increasing very fast. So it was getting very interactive. We failed. I definitely want to highlight in this talk, but we failed as well because that doesn't come out in a lot of papers. So we like the pure RL setup here failed because we thought it's a good RL problem that we can go ahead and like prove, and like that becomes a reward and everything is negative and the algorithm would evolve on its own and so on. But that didn't turn out to be the story.
So the problem is the number of clauses. Can you do some effective truncation so that the action space?
Yeah, we tried that. We tried a lot of those things. We spent I think 7 to 8 months around that. We were not able to make it work. There was a group at IBM which make it work in a limited setting, but it came up with a few caveats as well. That they started with from a good policy already. They didn't start from scratch. So they started from a heuristic prover policy. So we tried a few things, but I think if you want to start from scratch that I don't want to use any heuristic, then it is really difficult.
So the number of clauses needs to sort of grow to such a large extent that the action space becomes interactable.
Yeah. So we tried to change, like I think we were discussing in our group at that point, and we tried to change the problem slightly. And we were like that there are two settings. One is like this supervised setting, how people were trying to do machine learning at that point. So they had a training set of theorems where they will train, they'll generate data where they were able to prove, and then on a test set they will go on to prove those things. Like they will be given 5 minutes to search at the test time, and they would do. We thought like this is an exam setting sort of, and I think IMO setting is even that. It's like okay, you train on whatever, and in the exam you are given a limited time, you go there. We wanted to go to a research setting where we are like that. You are given these 100 or 1,000 or million theorems, you do whatever you want. How many times you want to try this theorem, whatever. We care about the final theorems. If you give more and more time to you, were you able to prove theorems which were not proven before and so on? Like so we given a pool of conjectures with no proofs. So we started with this hypothesis. So in that setting you need proofs. But here we started with no proofs. So you only have conjectures. You try multiple times on this. Whatever you generate, you learn from it, and then you continuously grow on this pool of conjectures. So the more you learn, the more you prove, the more data you have for learning, and the more you can prove. So we were in this what we call as incremental setting, in like the research setting. And here comes like a challenge as well, and here comes our idea of what we did actually in the hindsight experience deeply. So when we were doing this, that we can learn from like a pool of conjectures, and basically we are not starting with any theorems. What we observed were two things. One is that a lot of times where we were able to prove things, so it will give us a positive and negative example. So you have a proof. So you know that for this conjecture, this thing was useful and this thing was not useful. But where we were not able to prove thing, that attempt is totally wasted. We were throwing away that data. Like basically, like we were throwing away the failed proof attempt, and we were not learning anything. The question was, can we learn something from there? And I think this idea is very crucial, and it occurs in multiple other places as well. That learning from your failed attempts. It occurs in life, it occurs in your research as well. So learning from the failed attempts, that was one thing. The second was that if say, initially you have a set of very hard theorems, and you are not able to prove anything. So you don't have any training data now to train on. Like your classifier is bad because it has not seen a positive example. So how it will get kick-started? So we had this problem of like that you can't climb at that point. So then you need to design some sort of curriculum. You need some data of like easier theorems so that your machine learning system can actually see some positive examples. So there is the idea of this hindsight experience replay, which is a very pretty simple idea. I think, yeah, it occurs at multiple other places, but I think from where we knew was reinforcement learning. So the idea was that, say you are trying to reach a goal. What we do is in like these reinforcement learning domains, you have a starting state and you take actions, you want to reach a goal. And so the idea was basically, if you don't reach a goal, so that attempt was wasted normally. But with the hindsight experience replay, wherever you reach, say you're trying to go to MIT from here, you didn't end up at MIT, but wherever you reach, you make that as a goal for your training example. So at least you know how to reach at that point. And maybe slowly and slowly, you would get deviated towards like the actual goal where you want to. If you make these goals as nice from your failed attempts. So basically, wherever you reach, make that as goal and give that data as like, when I say that make that as goal, basically use that as a goal for the training example. So you have failed attempt, your goal is not reached. So basically make that goal in hindsight. So this is what we call as adapting the idea of hindsight experience replay to saturation based theorem proving. So idea was in the failed attempts, wherever you reach, you will turn those clauses as new conjectures because you know how to get a proof of it. The idea is very easily depicted in this picture. The successful attempts look like this, where you reached actually contradiction, you have positive and negative examples. But if in a failed attempt, like your attempt is wasted. But with hindsight experience replay, what we do is that wherever you reach, for example, this is the goal. And so you basically negate this clause wherever you reach. You put negative clauses at the top for this, and you create a new theorem basically where you know how to reach the contradiction. And so basically, like suddenly you are in this data-rich domain of like basically you can, from all your failed attempts, you can generate many more theorems, but it comes up with a caveat that you should select these goals very carefully. You can't select arbitrarily. And I think the idea what we used here, it was slightly more complex, but like the simple intuition is that since we want to reach contradiction, which is false, so again, we use the goals which are smaller here as the goals. We created a probability distribution of smaller clauses as like the failed goals. Here, and in the interest of time, so that Abbas has good enough time for this. So we did this. Now the question is how basically we fed this logical formula to neural network. There have been a lot of works on using graph neural networks, basically represent logical formulas as a graph and then represent that. What we did was instead like transformers were super effective representations. And with this, we also added this idea which came up concurrently in the machine learning literature. I think it was a concurrent discovery of using spectral features. I'm not going into the detail, but what we used was spectral transformers. So just in the interest of time, but if anyone wants to talk more about it, what representation we used, I would be happy to talk. Coming to the experiments and the results. So like there were 2-3 things, lessons in this talk, like we had this incremental learning, we created this research setting. Then this idea of hindsight experience replay, which is using the failed attempts. And the representation, a neural network was spectral transformers. So we compare with this eProver, which is like almost close to Vampire if you search online. And there was this work Trail, which uses reinforcement learning, which I was mentioning from IBM. And the eBasic is a very simple prover, which just uses this heuristic that the smaller clause is good as the cost.
Real quick, I know that experience replay is something common in reinforcement learning, but are you applying, I'm still missing it. You're not doing reinforcement learning with this incremental learning?
So we are not doing traditional reinforcement learning, but we took just this experience replay idea and converted that to us like the supervised setting. So again, we are learning a classifier, but this idea of using the failed attempts of like hindsight experience replay, we adapted that to a supervised setting. So that is
this is what's generating your pool of conjectures?
So this is like, so in whatever attempt we did, so every failed attempt also gave us one training point.
Yes.
So what is happening is that you are given a pool of conjectures, you are proving some things, and then you have a learner. Basically, this neural network is guiding your cube while proving things. Now, this neural network needs to learn from some data.
But it's generating more and more data.
Yeah, it is generating more and more data, and we are able to generate more data because we are using failed attempts.
So it's supervised experience replay with a growing active learning
Exactly.
data set.
Yeah,
Thank
yeah,
you.
yeah. So yeah.
Can I also ask a
Yes,
question?
sure.
Of course, there's an idea that is also close to how mathematicians
Yeah.
operate. And you try to prove something, it doesn't work, and you remember that, but you not only remember that something did not work, you also analyze why it didn't work.
Yeah.
So that is an important step. To what extent is that represented in your scheme?
I think yeah, like it's like these means the lesson was also like that. These first order logic proofs were very obscure. So I think like the related question probably which you are alluding to is that the set which you came up, that did it represent any useful theorems in itself or not? Because like whether we analyze, so we didn't analyze anything because the first order logic theorem proving data is very difficult. It's like reading assembly language in contrast to like say working with a C++ or Python here. So it's very obscure proofs. We started with this, but that is why like most of the later efforts in theorem proving moved to the higher order logic in Deepmind. So it's a bit difficult to look at. We tried looking at what we were proving and so on, but it was very difficult, or it's like reading assembly code. It was not that. But yeah, like the inspiration is coming from some of those things. For sure. So yeah, I just want to highlight, there are 3 data sets which are popular in this community. There was MPTP 2078, which is a set of 2000 theorems, which are slightly on the harder side for machine learning provers. So the E-best gets around 70% on that. Then there is the M2K, which is the simpler version, where I think like these provers prove almost everything. These are explicitly chosen as like and both these data sets are chosen from this Mizar 40K. So these are 40,000 theorems. There was a huge effort of like converting the mathematical knowledge into the Mizar data. And so we were able to outperform the E's best setting with these methods on, and E is pretty close to Vampire. We're not able to run Vampire internally, but yeah, this is where we ended up. We also analyze the proof lengths of our proofs, basically the length of the tree, like how long is our proof. And I think for 99% of our theorems, our proofs were shorter than E, which was pretty interesting. So on this X and Y axis, on the Y axis is our proof length, and on the X axis is E's proof length on these 2 data sets. And you see most of the things are below the Y is equal to X line.
Quickly for context, you mentioned earlier that you abandoned the RL approach directly because of the growing action space. But there was a heuristic approach that worked. Is that what Trail is?
Yeah, so it is using that action space, but it starts from the E's best setting. So it is basically, it takes a good heuristic system. So it's like you take the stockfish and then you add some machine learning on the top.
So they're sort of doing comparability to, naively speaking, but you're going really from scratch.
Yeah, we wanted to go from scratch. I think that was the thing, that we don't want to use the heuristics. It's like we wanted to go to the AlphaZero route directly.
Yeah.
And I think we also analyzed, so like combining the 2 approaches, how many unique problems were solved by ours versus E. Like, so there were some unique problems. So if we combine, I think if we will gain even much more. Yeah, so I think it is a good point to stop, and I will hand it over to Abbas to talk about disproving. But I would be happy to chat about it. It's slightly older in the first order logic, but I hope the lessons here could be applied in much more other settings. Yeah, over to you, Abbas.
Right. Yes. So what I want to do is kind of the opposite of what Ankit is doing. But if you go inside, it's really the same thing, just searching for something else. But the goal is really to find a counterexample to some theorem instead of proving them. But the spirit is very, very similar. So this is the button. Okay. And this is the yeah. So this is based on this paper, which appeared in Ichkai 2024. And you see you have many co-authors, and Adam, joint photo with Adam, who advised us on this work. And yes, so what are counterexamples? So counterexamples just mean you have many examples, and one of them just look different than the others, and you're looking for that exact one. So in a way, it's like finding a needle in a haystack. I don't know if you can see the different penguin.
There's the white penguin.
Yes. Yeah, so finding counterexamples by computers is very old. The first paper I was able to find is this 1966, which was a conjecture of Euler, which says you need at least n nth powers to sum to an nth power. And this counterexample was found. And this is the whole paper, just 4 lines. It doesn't explain, it's just an exhaustive search in the name of the computer. But yeah, so it's really not new thing, it's 1966.
Is that the shortest paper?
And this is the shortest paper I have found, but I don't have a proof. Maybe you should ask Guinness to add an entry. Yeah, so yeah, what is interesting? Why are we interested in counterexamples? Like, why did we start this project? Well, one thing is you just need one counterexample to kill the whole theorem, which is kind of fun. And it's easy to verify that it's a counterexample, but it's also very, very hard. You know, if it was easy, then other people would have found it, or the person who gave the conjecture would have found it. So it's really hard. And sometimes these problems are open for decades, like the 4-color conjecture was open for around 100 years. And you need some very clever search methods. So you cannot just do exhaustive search. Maybe for this one you could, but as the problems become more complicated, you need mix of computation, mathematical analysis, then computation again. So it's really very interesting how people find counterexamples using computers. So that's what motivated us to do the counterexamples. And so we focused on one particular method for finding counterexamples, which is based on reinforcement learning. So the idea was actually, the first paper was done by Adam using RL finding counterexamples. So the idea is to have an RL agent that keeps on generating a mathematical object, for example, a graph or a matrix or whatever. And then we have a score function that is designed by a mathematician and is coming from the mathematical conjecture. And if the score is large enough, that's a counterexample. So if, for example, you have a 0, and if the score is positive, that would correspond to a counterexample. That's how the score function is designed. And then we give this score function as the reward to the RL agent. RL agent doesn't know anything about the math problem. RL agent just wants to maximize the reward. Doesn't care what's the score function. So we keeps on trying to improve and improve and improve the reward. And hopefully at some point it will find a positive reward, which corresponds to a counterexample. So that's the overall setup. Okay, what exactly problem that we worked on? So we also worked on extremal graph theory because Abbas Mehrabian was an extremal graph theory. I also did my PhD in graph theory, so it came naturally to me to look at the problem from extremal graph theory, which in a way is about relation between global properties of a graph and local properties of a graph. Like global properties, you can think of the number of edges, number of vertices, or planarity, or whatever. And local structure is mostly about whether you have some subgraphs, like if you have triangles, or you have 4 cycles, or things like this. And it's the interplay between global and local properties that makes this really interesting. Particularly, we looked at the problem so-called extremal graph 5, which asks, suppose you have an n-node graph, and you know that it does not have 3 or 4 cycles. 3 or 4 cycles are forbidden, right? And how many edges can you put in the graph without creating 3 or 4 cycles, right? Very simple to state. So here's a graph which doesn't work because it has a 3 cycle, BCD, 3 cycle is not okay, and ABCDE is a 4 cycle. So it's not okay for 2 different reasons. But if you remove one edge, then you get this new graph, which is acceptable because it has no 3 or 4 cycles. So the answer for n equals 5 is exactly 5. And you can do by exhaustive search, you can see that you cannot have a graph with more than 5 edges. Okay, so Okay, this is easy for 5, 6, 7, 8, 9, 10. But if you, as you increase the number of nodes, the searches become so large that you cannot do exhaustive search, right? Also, this problem is interesting because of a Erdős conjecture from 1975, who conjectured that as n goes large, which is what we mathematicians are interested in, the number of edges, the maximum number of edges is at most this quantity, n over 2, 3 over 2, and he provided a construction with these many edges. So, so you found this construction and you conjectured that that construction is tight. You cannot add one more. Of course, I'm talking asymptotically. Now, this is a nice example. When n equals 50, you get this beautiful, beautiful symmetric graph called the Huffman singleton graph, which has 50 nodes, 175 edges, which has is around 1.4 times more than Erdős's conjecture. But this graph is really an exception. As the number of nodes increase to like 1,000, you cannot have this many, like 1.4 times this. You see that in practice, most of your graph have much less edges than this many. But what is interesting is that this is the only graph with 175 edges and no 3 and 4 cycles. And on this size, you have 2 to the power 1,000 graphs. And only one of them gives you the counterexample. So that's why counterexamples are so interesting. And accidentally, it's also a symmetric graph. So I don't know whether it's an accident or is it something about the nature of the problem that the counterexamples look very symmetric to humans.
What was this one found?
I think it's 56 years old. Huffman.
How?
I don't know. I have no clue.
There's a Wikipedia page on this. There is a Wikipedia page on this graph itself. So,
But this was before computers.
So the proof was constructed, or how do you know that?
That it's a single one? Okay, I don't know. This was proved long ago that for size 50, this is the optimal one. I think there's a proof without using any computer. Yeah. Yes. Okay, let's try to. Oh yes, so once this conjecture came, then people tried to proving it for, or at least finding the maximal graphs for different ends. And when we started work, it was solved up to 52. Like for all n equal 1 to 52, the maximum number of edges was known. And as we were working, I think last year, it was also found for 53. What is the maximum number of possible edges for size 53? But for larger than 53, it's open. Like there are lower and upper bounds for how many edges you can put, but the exact number is not known. So that's the threshold where all the exhaustive search and all the clever searches, they cannot give you the exact answer. And in terms of asymptotics, the best known bounds is due to Garnick, Harris-Cohen, and Lazebnik, which prove that this limit, so f of n here is the maximum number of edges you can put in your graph without having 3 or 4 cycles. If you divide by n root n, the limit is between 1 over 2 root 2 and 1 over 2. Erdős conjecture is that this is actually an equality. So the limit is equal to the lower bound. That's the conjecture. But as you see, there is a gap of around square root 2 between lower upper bounds. So that has been open for almost 50 years. Okay, so with computer methods right now, we cannot approach the asymptotic problem. So we thought, okay, let's look at the small cases like fixed n. What we can do? Can we like find graphs with more edges than known before? Or I don't know, n equal 100, for example. We put the target 100, 200, these values to see what we can do with that RS. So, okay, so let's go back to the setup now. Going back to the setup, the object is now a graph. The score function is very easy to define it. For example, you can put something like number of edges minus number of 3 cycles, number of 4 cycles, because yeah, you want to give a positive reward for this, and you want to give penalize for 3 and 4 cycles. And it's not hard to see that if you have a graph with a score 200, then you can easily turn it into another graph with the same score without 3 and 4 cycles, basically for every true or false cycle, you have to delete one edge, right? So the score is very natural, corresponds to what we need. Okay, let's see. Yeah, these are the new. Okay, so how can we generate a graph using RL? There are many ways. Like you can ask the agent to produce the graph in one go. Just show me a graph. Okay, that's single shot way, which is very non-flexible because it does not have possibility to correct or I don't know continue the generation. What is more smooth is just have it generate the graph in several steps, which is very typical in RL that you give it several steps and okay, you have, I don't know, 200 steps to give me a graph. So let's do it iteratively. But again, there are different strategies to generate the graph, which I will explain next. What we do is we do this edge flipping environment, meaning that we start from some initial graph and each action is to choose a pair of nodes and flip the edge. So if the edge exists, you delete it. If the edge doesn't exist, you add it. Okay, very simple process, but it's very powerful because you can generate any graph from any graph if you give n choose to number of actions. Okay, so very not small action space. Action space is n squared, and the horizon length is also around n squared. We found this one to be a good balance between the number of actions and the horizon. So for example, if you have this graph, you choose like the action chosen by agent is AD, then you get to this graph. Now if the action chosen is CD, then you go to this graph and you repeat this process over time. And here the action space is fixed. The horizon is something you need to tune by hand, by trial and error, and see what is a good horizon. I think we tried many horizons to find a good one for our purpose. Okay, so as a baseline, okay, we thought, okay, this is very cool, but we need to compare it with the baseline, right? So as a baseline, the most important baseline for this problem has been local search on graphs. There are different types. There's simulated annealing, taboo search, iterated local search, and stuff. But we looked at taboo search as our baseline. So how does taboo search works? So you have different states, and each action makes a local change to the graph to go to a new state, and then you continue this operation. So you do local changes, which is really flipping edges from going from one state to another, and you keep a set of forbidden sets. So the issue with many local search algorithms is that you might get stuck in a local optimum. For example, if SI and SI plus 1 are good states, you keep on flipping between these two, and you will get stuck. You will not get out of this local optimum. So the way taboo search handles this is this does not allow you to repeat your last action, right? So for example, if this is your graph, this keeps a set of forbidden set of edges. Let's say size is 3 in this case. That's also a hyperparameter. It says you are not allowed to flip AB or BD at this stage. So let's say you choose randomly, you choose your actions randomly, right? You choose randomly to flip AD. So you flip this edge AD. Then you add this AD to your forbidden set. So in the next iteration, you cannot flip AB, BD, or AD, right? Out of these 6 actions, 3 of them are forbidden, but between the other 3, you choose randomly. So in a way, it's a very, very simple algorithm, but very, very powerful. And this simple forbidden sets allows you to get out of local optimum.
Do you somehow add this to your state, or otherwise you break the Markov property?
So do you add, oh, sorry?
Break the Markov property of the decision process by doing that.
Yes, yeah, it's not, if you want to define it as a Markov property, you need to contain the whole state plus the forbidden set as your state.
Can you do that?
Yes, yes, we can do that. And this set is first in, first out. So if when it fills, you throw out AB. So it's a fixed size. So as you put and new ones, you let the last one out. Yeah, exactly. Okay. Okay, but what RL agent did we use? We need to make it like decide about an agent. We tried many different agents, but the one that we ended up, which is the most powerful one, we tried is AlphaZero, which is based on the Monte Carlo tree search. Right? So, yeah, so it basically, I won't go into a lot of details about this, but it basically keeps a tree and it starts from some starting states and builds a tree of actions. As you do actions, you go down the tree, and then you want to give, and the leaves of the tree correspond to the final graphs that we achieve. And somehow you have to choose between how to choose the next action. If you choose randomly, it's useless, and you start from random search. But as you learn, somehow you learn how to guide the search through a good action, and that is the learning process happening. That's the AlphaZero part. So you use neural networks for learning good policy, like which action to choose, and a good value network, which tells you from this node what is the value of each of these children. Right? And when you reach a leaf, which gives you a final reward, then you propagate this information back, then you update the reward and policy and value networks. And it also uses the UCB formula for balancing exploration and exploitation. Right? So in our case, our state is the graph, the actions are flipping edges, and the final reward is the score. The reward in each step from going these children, from going the parent to the child is the difference between the scores. So the final reward when you go to the leaf would be the score of the final graph minus the score of the starting graph. But okay, but we tried this, it did not work very well. The crucial idea which helped, which is similar to what Ankit explained, where you somehow want to increase the learning difficulty little by little. So that's the idea of curriculum or training on examples of increasing difficulty. And here it's very simple, because many of the times the graph of size 50, the best graph is a super graph of the best graph of size 48. So when you want to generate the full graph, you don't start from scratch. This is what we starting from empty graph and try to generate the full graph. But we very soon realized that it's much better to start from a graph of a smaller size, which is good, and then adding 2 isolated nodes. So then we created this data set of high scoring graphs for size n. We keep the data set for n plus 1, n plus 2, and n plus k. So when we want to generate a graph of size n plus k, we choose one of these numbers randomly, and we start, for example, from G3 n plus 1. We add some additional nodes and then run the agent and the taboo search, both of them, from this starting graph. And this had a huge improvement on the results. And this search method can be either local search or AlphaZero. We can do this idea for both of these.
Just make sure I understand the outcome. When you say you run the agent and taboo search, you mean as you go along, you're keeping track of these forbidden sets and just making sure that you don't revisit something new.
Yes, so that is done. So these are 2 separate processes. Once you have this starting graph, then you give this graph to taboo search, and taboo search does the handling of the forbidden sets. So taboo search runs for 100 steps, and during that 100 steps, it keeps track of those forbidden sets, and it finds a final graph. Then if the final graph is good, then we put it back in the data set. So when we put the graph in the data set, then we forget about the forbidden sets and everything. We just care about the graph. Yeah. Other questions? So here are the results. So here, what I want to emphasize, so the thing is, we get very similar results with taboo search and with AlphaZero. So that's in a way saying that the learning did not help much, but the curriculum idea or the incremental idea helped significantly. So here's on blue, you see the taboo search result. With that dotted one is the one which you don't use the incremental for the curriculum, and the solid one is when you use the curriculum. And in this, the green is the same for alpha 0, and you see the solid ones are very identical, but the dotted ones, you see the dotted one is much worse for alpha 0, and in taboo search also slightly worse. So the most gain came from using this incremental idea, which was, in a way, we didn't expect this. We thought that, okay, machine learning will be help a lot and will easily defeat taboo search. So in a way, it's another example of, okay, it's not that you add learning to your problem and it magically solves it. Many times there are other ideas which come from, I don't know, mathematical intuition, which will help you get the result you want. So that would be the main lesson.
Can you say one more time how you do the incremental part of the alpha 0? I've heard about goal-based reinforcement learning before, but I've never really understood exactly how it works. Are you altering the function or?
No, we switch as a starting state. You see, we have to have a starting state in alpha 0. Now the question is how you choose the starting state. The first idea is always start from the empty graph of size 50, right? And then learn based on that. So what we did was, for choosing the initial graph, we have a database of graph of size 45, 46, 47, 48, 49, which have good scores. We sample one randomly from there, and we choose that as our starting state. And then train based on that.
Okay. So it's just a modification of the starting state.
Very simple modification.
Okay.
Yeah, it's too simple that you don't know why it's giving so good result, but it's kind of building up on your learning as you go. And so we slightly improve the state of the art. So the red results are the state of the art results, and so the yellow is the upper bound for the problem. The blue is Erdős conjecture. So if we stay above the blue the light blue forever, then we will disprove it. But as you see, it's going with a very slow speed going downwards. So probably this will not disprove the conjecture. But we were able to slightly improve the state of the art, which is the red curve. And yeah, so incremental taboo search and incremental alpha 0 got roughly similar results. So I haven't shown them because they will be really identical, except for 2 or 3 sizes. Yes, so maybe we can discuss a little bit. Can we disprove this conjecture using these methods? Probably not. So when we started this project, we thought that maybe the graphs will give insights to mathematicians to generalize, to build an infinite sequence, because for disproving, we need an infinite sequence. But honestly, these graphs are so complicated and so hard to understand that it would be very hard for a mathematician to come up with a pattern in this. But what we learned from this work is that how strong RL is against local search, and where, for example, RL really does not help much for this problem. And could be potentially the methods we developed, this curriculum idea may be used for other problems as well, because it's very natural that your problem as size n depends on your problem as size n minus 1. Yeah, I think the key is that the curriculum was key to making the process for this problem, both for alpha 0 and taboo search. And the main message is sometimes it's really hard to make machine learning methods work well. Thank you so much.
Yeah. So you started out with Euler's conjecture for exponent 5. Have you tried Euler's conjecture for exponent 6, which is still open?
Oh, nice. I should write that. Yeah. No, we haven't.
No progress. I mean, LP's found an infinite family for 4, but no, as far as I know, it's open for every n bigger than 5.
Wow. No, I didn't know about this. This is a very cool conjecture.
And yeah, maybe just to advertise the problem. I don't think the last effort on this was, I don't know, maybe 10 years ago. Just throwing more compute at it, you could go a lot further, but it would be very cool if
maybe there could be learning happening along this 5, 6, 7, like studying these problems together may provide more insight.
So I would imagine people have thrown computer added and sort of ruled out the first whatever.
Yeah, I think they've looked for solutions, if I remember right, up to, there's no solutions with where all of the values are below 800,000.
That's without them. So.
Without trying to do anything clever, just an exhaustive search.
Nice, nice. I haven't thought about this. It's a good suggestion.
But anyway, the space they've searched exhaustively is much smaller than 2,000. So
Yeah. Yes.
I have some question about this respondent, how one could approach it. So here's this example, what we call the Hoffman graph for n equal to 50.
Yeah.
Of course, if you combine several of them, just join them also get examples for higher values of n. But probably asymptotically that doesn't really give you anything better.
Yeah.
But on the other hand, instead of starting with an empty graph and adding edges, could also start with a complete graph and try to delete edges and see which is the smallest number of edges that you need to delete in order to get examples of this extremal girls 5 graphs.
Yes.
Did you attempt that as well?
Yeah, we tried that. Do you remember what was from the complete graph, starting from complete?
Yeah, I think it is exactly the same problem. Like for the machine learning, it is just a representation, whether you're starting from 0 or 1.
Yeah,
so like a neural network.
Of course, there's some duality in graphs here that you can
but one thing which, like when we published, so this data set is public, like all the size, all these graphs are public. So somebody used these graphs to construct, like say the graph we found at size 70, to generate a graph, a better graph, even better what we have achieved. So it is David McKay,
Brendan McKay,
on like to get a smaller graph. So they did like the incremental sort of like the decrement, like start from our graph and then which we had not, but they improved that, like he shared that with the bus.
So this n equal to 70 graph is geometrically very different from the n equal to 50 graph.
It is very different. So 550 is really very special. And for size 51, is most cases you add 1 or 2 nodes.
Pending nodes.
But this symmetric graph does not exist or any size greater than 50. I mean,
but I mean, for n equal to 100, you just connect 2 of them.
It's very hard to combine because you want to avoid creating triangles at 4 cycles. I don't think there is a natural graph product that maintains this property.
Yeah, but if you just connect a couple of vertices and then 2 copies,
you're looking for n to the 3 halves, so you need a lot more edges when you connect.
Sure.
Yeah. So like that will give you 2n. Two means like, but you need n root half. So that will not give you. That is a very weaker lower bound at that point.
This construction uses projective geometries of certain size, so it's a very global construction. It doesn't build up from scratch, and only exists for n that is prime powered or something like that. So it's really some very global geometric construction.
Can I ask a question about the theorem proving contests? I assume these are all done under some time limit or a compute limit.
Yes.
I was curious how much, like if you increase the compute limit by a factor of 10, how much improvement do you expect to see?
I think I didn't highlighted those results. I just want to, like somebody's online. So the question was basically like how much if we increase the time limit or compute limit to. So what we did, I described this research and exam setting. So the exam setting was like, okay, mostly these provers were run for 5 minutes and 10 minutes because they were competing in this competition and that had these 5-minute limit on each theorem. So they super optimized, okay, that in 5 minutes we wanted to go crazy on it or like, but what we did was this, we gave it a bunch of conjectures of like, which are not, which have no proofs. And we let it run for 7 days. Like the whole learning process is like we throw, but I think the gains are very, very marginal beyond that. So I think we extracted, I think that is the unfair advantage of Google, whatever. We extracted that out that if we threw more compute. But these ideas like these were systems isolated. But I think the more recent systems are that where you use the whole world's knowledge with a language model, like what people are doing in alpha proof and which is like, where you can use much more. But yeah, this is like, I think for this problem, we exhausted. We ran for 7 days and we compared by running those like C++ based systems as well for 7 days. So yeah.
So more compute with the project code.
No. We thought like, yeah, that is what we like after 7 days, yeah, it was like one theorem is arising in a day or something. So that was not worth it. Like if we are not seeing a jump, like it was very incremental.